Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on IGA. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Dr. Rajiv Soman, Director of Purity Survey at EAG Laboratories, will be answering some of the questions during the presentation, and we'll also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Dr. Jayesh Kumar Das, Specialist at EAG Laboratories.
Hello, welcome to today's webinar. Today we are going to talk about instrumental gas analysis, also known as IGA. My name is Jayesh Kumar Das. For over 15 years, I have been using gas and their isotopes to characterize a variety of materials. In 2018, I joined EAG as a specialist. Prior to that, I actively pursued research in field of cosmochemistry, trying to understand origin of our solar system and moon by analyzing meteorites and sample collected during Apollo missions. At EAG, I continue to analyze variety of materials using various chemical analysis techniques, including IGA, today's webinar topic. This is the plan for today's webinar. After a brief introduction about EAG, we will talk about why we need to characterize any material. We will briefly see how to use EAG Smart Chart to find a suitable analytical technique for your materials characterization need. Before presenting some real-world examples, we will quickly go through fundamentals of IGA technique and some basic operation principles. After few real-world examples, in the end, we will summarize strengths and limitations of IGA technique. Eurofins EAG Materials Science is providing high-quality scientific services since 1978. With 16 laboratories and 5 business development locations in over 20 countries, we serve more than 4,000 clients from various industries. At EAG, more than 600 qualified, highly educated, skilled employees are using industry-leading state-of-the-art technology and taking advantage of scientific and engineering know-how to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. We have 4 state-of-the-art IGA laboratories located in Syracuse, Toulouse, Eindhoven, and Shanghai to serve our clients worldwide. As highlighted in this flowchart, our innovative approaches to problem solving are key to solving commercial challenges from concept through commercialization process. Client success requires control and optimization during all steps that range from research and development through failure analysis. EAG provides the knowledge and appropriate tools for clients' success. This slide shows the IGA instrument that we have at our 4 different locations. We have total 16 IGA equipment in operation where analyses are done on a daily basis with strict quality control. Our quality system include various accreditations. For example, our Syracuse location has ISO 9001, ISO 17025, and GS 400 certification. This slide gives a simplified schematic for why do we need to characterize a material and how can we characterize? Well, several requirements can drive material characterization, like ever-increasing regulatory compliances or supply chain requirements, purity certification, and maybe technology innovations that lead to new kind of engineered material. The next question is how to perform required characterization. The answer is using an analytical technique, or many times combination of analytical techniques. Broadly, these techniques can be characterized as two types: spectroscopy techniques and microscopy techniques. Due to continuous innovation, these analytical techniques have expanded our capabilities in terms of detection limits and analytical resolutions. As a result, we now have a range of analytical techniques that many times it is difficult to select an appropriate and effective analytical technique. One solution could be using the EAG Smart Chart. What is Smart Chart? It is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool. The Smart Chart offers a concise visual reference for comparing analytical techniques, permitting one to compare detection limits and analytical resolutions for numerous material characterization techniques. This include evaluation of surfaces, purity surveys, and more. Each bubble or bar represents different analysis technique. Surface analytical techniques are represented inside the box, and bulk techniques are represented outside the box on the right here. Imaging techniques are represented below the box. Bulk techniques on the right have range of detection limit, whereas the imaging techniques have the resolution limits given as the x-axis. The color of bubbles also have meaning as listed in the lower left corner. For example, the blue bubbles represent technique that give elemental information. In this webinar, we will focus on IGA techniques and how it can be used for material characterization. The useful region of IGA is depicted here in this blue box, which can measure certain gas-forming elements in a sample at levels ranging from 1 parts per million to as high as 100 atomic weight percent. So the question is why to use IGA technique? So when we consider final manufactured products such as automobiles, aircraft, medical devices such as pacemaker or cochlear implants, or devices used in space and defense applications, most of this in final product are most of these final products are engineered and manufactured from raw materials like oxides, hydroxides, carbonates, nitrates and nitrides, sulfates and sulfides, and carbides. These raw materials are mostly found in Earth's crust as in form of minerals. These raw materials goes under extensive range of processing like purification, refining, and enhancing as required by specific application of the final products. Sometimes after going through all these steps, a final product may fail to perform the expected operation. This brings us to other critical segment of material characterization, and that is failure analysis. As can be understood, application-driven characterization is therefore necessary for these materials. One of the aspects of material characterization is analysis of gas-forming elements. These elements reside in sample either through chemical bonding and/or trapped in lattice structure as gases. These elements are mainly hydrogen, oxygen, carbon, nitrogen, and sulfur. IGA technique is an industry standard for analyzing these gas-forming elements in steel, metals, and alloys. The other fact I would like to emphasize here is that IGA technique can also be considered as a subset of gas analysis, where we can precisely measure oxygen, carbon, nitrogen, sulfur, and hydrogen. On the other hand, IGA can also be a good complementary analysis for bulk and trace elemental analysis that can complement to the analysis like glow discharge mass spectrometry analysis or inductively coupled plasma mass analysis. On the other hand, IGA can also be complementary analysis for evolved gas analysis or outgassing studies. Let's begin with fundamentals of instrumental gas analysis. To understand this technique, we will broadly divide it in two parts: gas extraction and detection of released gases. Gas extraction critically depends on how sample preparation performed, what is sample's weight, and what type of crucible we are going to use. Extraction also depends on what type of extraction and optimization method is being used. On the other hand, detection of gases depends on weight and matrix of samples, enhancing gas signal by removal of unwanted gas species. The other important parameter is which type of detector we are going to use for detection of these gases. Sample preparation is probably the most critical step in IGA technique, especially if we want to have very low detection limits. Also, sample preparation depends mainly on sample matrix as well as which gas we are interested in measuring. In general, sample preparation can be accomplished in four steps. Using a high speed saw, we cut the sample in appropriate size. While cutting, water cooling is used to minimize or avoid gas loss from sample due to heating. If needed, sometimes chemical etching is performed to remove surface contaminations and coatings. Similarly, polishing can also be used to remove surface oxidation. A solvent cleaning is performed to remove any contamination that might have occurred during sample preparation, followed by drying. The most common example could be copper matrix, where we need to remove oxidation layer, followed by etching in an acid, and then keep the sample stored in acetone until we are ready to do analysis. The powder samples do not require any preparation as such and normally packed in capsules for analysis. However, relatively less complex sample preparation is one of the strengths of the IGA technique. The next step involves sample weighing. Precise and accurate weighing is mandatory since final measurements are provided in microgram per gram or weight percentage. Two types of crucibles are used for gas extraction. Crucibles are often pre-burned to remove any gases in crucible absorbed during storage. Also, note that ceramic crucibles are used for carbon and sulfur analysis, whereas graphite crucibles are used for hydrogen, carbon, and nitrogen analysis. On this slide, we are looking at two different methods that can be used for gas extraction. Inert gas fusion can be defined as gas extraction performed in inert gas environment. For example, sample is heated in graphite crucible in presence of helium or argon. Sometimes a known amount of flux material is used to enhance the extraction by lowering the sample's melting point and promoting chemical reaction to optimize gas release. The method is mainly used for oxygen, nitrogen, and hydrogen analysis. On the other hand, the method of hot extraction, where sample is heated below its melting point. Under such condition, the sample would still release gases, mostly trapped gases that can be analyzed. This method is somewhat similar to doing outgassing analysis. The only difference is that most cases outgassing analysis are done in vacuum. The next gas extraction method is combustion. In this method, the goal is to combust sample in oxygen environment. Sample is heated in ceramic crucible in presence of oxygen. Different type of flux material is used that can promote oxidation and lower the melting point of sample. This method is used to analyze carbon and sulfur, which are detected in form of CO2 and SO2. Now let's talk about detection method. The first method is using an infrared detector. This type of detector works on the principle of light absorption. An IR emission through an infrared source passes through a sample gas chamber. Based on presence of gases, specific absorption takes place. The absorption is a function of the vibration energy of that gas molecule. For example, in case of CO2 molecules, the absorption would occur at wave number 2350. Infrared detector at the end would detect a spectra somewhat similar to spectra as shown in the lower right corner. Using Beer-Lambert law, by comparing incident light, light and absorbed light intensities, one can calculate molar concentration of gas responsible for the absorption. The other method is based on detecting thermal conductivity difference using Wheatstone bridge arrangement. Thermal conductivities of reference gas, usually a carrier gas, and sample gas is compared to determine the concentration of sample gas. It is therefore necessary to have a very different thermal conductivities for sample versus reference gas. For example, to detect nitrogen, helium carrier gas is suitable, whereas for hydrogen, argon should be used. This schematic shows a typical experimental setup to extract and detect oxygen, nitrogen, and hydrogen. As can be seen, after extraction, gases pass through a filter, mostly a particle filter, and uh, of optimized by different ways before the analysis. When during inert gas fusion using helium, first oxygen is measured, followed by hydrogen, and then nitrogen. Lower panel shows an example of using argon as a fusion gas and performing hydrogen analysis. As can be seen, hydrogen can be detected by both detection methods, infrared detectors and thermal conductivity detectors. Similarly, this schematic shows a most common setup for doing combustion extraction for the analysis of carbon and sulfur. For example, to enhance oxidation number for released gases, copper oxide catalyst is used just before analysis. At EAG, IGA testing can be broadly divided into two categories. Traditional way, where well-defined ASTM methods are used to analyze conventional samples like steel, titanium alloys, and refractory metals. The other category of testing where we utilize the power of IGA. These testing methods are generally developed as per the client's requirement and normally performed on unconventional samples like non-ferrous metals using methods beyond standard ASTM methods. Accuracy and precision are the cornerstones in evaluating any analytical technique. Let's understand the difference in accuracy and precision by using a simplified schematic. We are going to look at various possibilities that may arise when we try to understand the behavior of measured values on y-axis with respect to number of measurements on x-axis. In first case, the measurements are showing widespread. That indicates that there is neither accuracy nor precision. The second possibility is where the measurements may have less spread. If we take average of these measurements, the average would be close to the certified value. This case could be the case of having accuracy but almost no precision. It is important to note that in real life example, this is probably the most common behavior observed for measured values. The third case could be where measured values have very good repeatability, indicating that measurements are precise. However, since the measurement are not matching with certified value, the measurements are not accurate. This could be a case of a systematic bias, and by using an appropriate correction, we may be able to make the measurements accurate. The last behavior is like an eternal bliss, as one of my colleagues likes to say. The measurements are perfectly precise and accurate. So let's look at the real data here. This table gives an example of how EAG measurements compare with certified values of hydrogen, carbon, sulfur, oxygen, and nitrogen. The average represents our internal statistical process control data acquired routinely for reference materials. As can be seen, the z-score is close to 0, means the difference between EAG average values and the certified values are very little. Please note that the Z-score is normally calculated using 1 sigma spread. Also, these measurements are done using ASTM methods. The data confirms that IGA equipment at EAG can produce accurate and precise measurement for well-established methods. In addition, the same equipment can also be used for method development and achieving similar kind of accuracy and precision for unconventional sample. So now let's begin with some of the case studies where what we have selected for this webinar. Now this technique, what we are doing is measuring hydrogen in the FBR polysilicon. So what is FBR polysilicon? It is a polysilicon grown using a fluidized bed reactor. There are mainly three types of purity grade in silicon: metallurgical grade, solar grade, and electronic grade. To produce solar grade silicon, normally a metallurgical grade silicon is used as a precursor material. A FBR process, relatively recently developed refining process, is used to grow solar grade silicon as shown in this schematic, where silicon vapor is created in the reactor by using silicon and hydrogen that deposits on the seed particles that that have been fed from the top. When you look at the microstructure of this, so after certain threshold value, you will grow 1 to 3 mm of polysilicon grains. Now, when you look at the microstructure of the bead grown in FBR reactor, it is somewhat looks like this. It shows a tree ring structure suggesting layered growth to silicon in hydrogen-rich environment. One of the research studies investigated different structure in these beads. The Fourier transfer infrared spectroscopy clearly shows the difference of and confirms the bead A and B have the presence of hydrogen bonded with silicon. As you can see here, where grain C doesn't have any feature, and the intensity for that particular grain falls in on this line as well as on this orange line over here. Whereas for sample A and B, you can see a clear release of intensity where you can differentiate the release of silicon and hydrogen, specifically hydrogen, based on the energy difference, bond energy difference for this different bonding. And by using this particular feature, we can probably try a fractional hydrogen analysis using IGA technique. So here in this example, we performed the hydrogen fractional analysis on similar polysilicon sample. We heated the sample in steps. As can be seen, varying hydrogen intensities corresponding to various silicon hydrogen bonds release with each temperature step. This clearly shows that fractional hydrogen analysis can not only differentiate the source of hydrogen, but also estimate the amount of hydrogen linked to each type of silicon hydrogen bond. The next case study is about high temperature outgassing of carbon fiber reinforced carbon composites. Our team has an excellent white paper that describes how combination of various techniques can be used to analyze ceramic composites. CFRC stands for carbon fiber reinforced carbon composites, also known as carbon-carbon composites. This composite can have variety of physical properties based on various designing aspects, including what type of individual components are used, how these components are layered, how the fibers are oriented within these components, and the way all these components put together as an end product. As can be imagined, the end product is bound to have complex architecture. Therefore, survey of chemical purity is essential to achieve desirable mechanical properties, reliability, and lifetime. One of the critical required information is carbon, hydrogen, oxygen, and nitrogen composition and their outgassing properties at high temperature. In this example, we will show how IGA technique can be used to derive such information. On this plot, oxygen concentration in composite is compared with heating time and temperature. The distinct outgassing profiles observed for carbon monoxide and carbon dioxide, two main oxygen-containing species, clearly shows presence of different oxygen chemistries and also provide guideline on how deoxygenation occurs for this composite. The table gives concentration of carbon, hydrogen, oxygen, and nitrogen measured using calibration performed by analyzing NIST traceable oxygen standards and also by using ASTM methods. As you can see, we are able to achieve a very good RSD values which enable us to do additional evaluation on this composite by using hydrogen to carbon ratio. Xiao et al. Showed that the hydrogen to carbon ratio can be used to predict aromatic cluster sizes by producing biochars using diverse ingredients and systematic processing in their experiments. In this table, they provide a relationship between the dimension of polycyclic aromatic ring and hydrogen to carbon ratio. If we compare our result, the analyzed composite seems to have slightly greater than 500 rows and columns of benzene rings per graphene sheet. This case study is about nitrogen analysis in silicon carbide sample. To optimize the clear extraction of nitrogen, nickel capsule and niobium flux are used. Let's see in details. Nitrogen often serves as a donor in silicon carbide crystals that are used in high frequency, high temperature, power, and auto electronics. Precise doping of nitrogen is necessary to manufacture various quality of silicon carbide crystals. However, conventional IGA method for nitrogen analysis cannot be used since at high temperature, melting silicon carbide with nitrogen will produce silicon nitride and carbon nitride, resulting in improper nitrogen extraction. The solution can be found by using a catalyst which can form carbide and destroys silicon and carbon nitrides. Refractory metals can play this role. Due to its low melting point and low volatility, niobium is a preferred catalyst. In this method, silicon carbide sample is packed in nickel capsule along with niobium flux. Using graphite crucible, the mix is then flash heated up to 2200 degrees Celsius. The outcome would be mostly niobium carbide, silicon, and nitrogen gas, which can be that can be analyzed. In this plot, x-axis is showing number of measurements, while y-axis shows nitrogen weight percentage. As can be seen, our measurement for certified reference material for number 360 yield a value of 4.72 plus or minus 0.27. Sorry, that is the value for our EAG average. The certified value is 4.77 plus or minus 0.05, and which is close to the EAG average value. In the table, we did another comparison where reference material is compared with an actual silicon carbide sample. Please note that when we attempted to measure the nitrogen without niobium flux, we could not detect nitrogen. Whereas with niobium flux, our results shows expected presence of nitrogen for reference material and as well as for the sample. Let's move on to our next case study. This case study talks about measuring carbon concentration in carbon-rich materials with high precision. As shown in this process chart, carbon fibers are made from acrylic fiber, which contains approximately 68% of carbon. After carbonization and graphitization, carbon fibers are made with high elasticity. Therefore, the elasticity of carbon fiber depends on carbon percentage in carbon fiber. For example, fibers with standard elasticity have 90% of or more carbon with nitrogen as secondary element. Determination of carbon weight percent therefore becomes essential to verify uh, the quality of carbon fiber. Let's see how can we use IGA for such measurements. To achieve high precision, a different approach is used. In standard carbon measurement method, we analyze blanks, then certified reference material, and then sample. However, for high precision measurement, we adopt stricter statistical approach where after analyzing blanks, we do analysis of two reference materials. One reference material that has higher carbon concentration than the expected concentration in sample. The other reference material has lower concentration than the expected carbon concentration in sample. After that, we do more replicates for sample than we do for standard method. The last step involves using a reference material with concentration near to the measured concentration in a sample. This is done to verify instrument drift, and if we detect an instrument drift, the entire method is repeated. For comparison, the standard carbon measurement analysis for a sample can be completed in, let's say, 30 to 40 minutes, while high precision method take more than 2 hours to accomplish one sample. Let's see some real-world data obtained by following this method. The x-axis shows number of measurements, while y-axis shows carbon weight percentage. The real value on y-axis are more than 98%. As can be seen over a period of more than 3 years, the data collected for real samples show remarkable consistency in precision and accuracy, validating the method for determining more than 98% of carbon with high precision. The next case study is about free carbon analysis in silicon carbide powder. Among wide range of applications, one of the application for silicon carbide powder is its use as an abrasives. The free carbon concentration in silicon carbide powder can decrease the hardness and their heat resistance. Therefore, measuring extremely low concentration of free carbon in silicon carbide is necessary. To perform free carbon analysis, there are some prerequisites. The heating should be done in quartz tube instead of using the more common ceramic tube or crucible. This is because ceramic, due to their permeable nature and structure, can interact with released carbon and could affect the final measurements. The other prerequisite is using a furnace where temperature can be raised by following a specific heating rate. This is usually done with a precision of plus or minus 5 degrees Celsius by using a programmable temperature controller. Such furnace would enable us to perform heating in steps and with desired ramping. Generally, for detection of free carbon, we use infrared detector. Measurement results of free carbon concentration in different silicon carbides as well as real samples are shown in this table. The gas extraction was done between 300 degrees Celsius to 1000 degrees Celsius with heating rate of 100 degrees Celsius per minute. As can be seen for the standard values, our method yields better percentage RSD values when compared to certified reference values. And also we have shown some real sample example where we were able to measure free carbon at the value of like 66 ppm. So this brings to the end of the presentation. Let's summarize strengths and limitations of IGA technique. As discussed, the sample preparation is relatively less complex. IGA is a quick analysis where sample can be analyzed in 20 to 40 minutes that includes blank, reference material, and a sample. This gives us high throughput in analysis. As we mentioned, the IGA technique is well-established technique for analyzing gas-forming elements in steel, metal, and alloys. In addition, we can do through case studies as we have shown. By developing new methods, we can use this method for composites and other applied materials. The other strength is ability to have a wide measurement range from almost 1 ppm to 100 weight percentage. Based on the series of data we looked at today, EAG can provide precise and accurate measurements. The limitations are listed here as first one is the destructive analysis. We lose the sample while we extract the gas because we completely melt the sample. The other limitation is we sometimes need large sample size if we need to measure trace level element. So why choose EAG? There are several reasons, the most important being client confidentiality is core to our business. We are global leader for materials testing services which with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. We have an extensive knowledge base and skilled expertise that enable us to offer multidisciplinary approaches that can be scaled to client-specific needs. Finally, in light of the pandemic that is affecting us all, EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local government, as well as the Centers for Disease Control and Prevention. Currently, all of our locations throughout the world remain open. We encourage you to discuss your options with our sales representative. Here is a partial list of upcoming webinars. You may register by using the provided link. Thank you.
Thank you very much, Jayesh Kumar. That was a great talk. As Jayesh Kumar mentioned, that we do have some upcoming webinars on the schedule, including one scheduled for tomorrow on precession electron diffraction. I did include some links in the chat window, so please visit those and reserve your spot. We're now going to begin answering the questions submitted during today's presentation. Again, we have Dr. Rajiv Soman joining us as our moderator during the Q&A session. As a reminder, you can still submit questions through the questions panel in the bottom right of your screen.
Thank you, Reena. Jayesh, there are a number of questions that have come in, and we will start with the first question. Is IGA analysis applicable to metals only?
Yeah, that's a good question. IGA can be used for a wide range of solid materials. IGA equipment have been traditionally used for metals and alloys, which are the most common samples. However, as we have seen in few of the case studies, that IGA can also be utilized for like ceramics, composites, carbides, and most other solid inorganic materials.
Thank you. The next question is IGA analysis different from outgassing analysis? And if yes, how is it different?
Yes, IGA analysis is different than outgassing analysis. For example, in IGA, we focus on certain elements and do the extraction in presence of gas environment, which is at some constant pressure. On the other hand, outgassing analysis, in that we analyze large range of masses from let's say 1 to 200 atomic units, and the extraction is done in the vacuum. On the analysis side, the difference would be outgassing analysis mostly would yield the results that gases that are mostly trapped inside the solid, as most of the time there is no complete melting. Whereas in IGA, we are talking about complete gas release, including trapped gases as well as gases which resided in sample with chemical bonding, since we are melting the entire sample. So yes, they are very different analysis in terms of what we get, what kind of information we get, and also how we perform the analysis.
Thank you for this excellent answer. The next question is, can you perform moisture analysis also?
Oh yeah, this is a good question. Yes, we can do moisture analysis, but it would be at most, we can say semi-quantitative, since what we do, just like the example we have seen in fractional hydrogen analysis case study. So based on the release of hydrogen from from a different bonds, what we do, we take the difference of total hydrogen release and with respect to the hydrogen release from the OH bond, the hydroxyl bond. And based on that difference, we can estimate the amount of moisture in a given sample. But here I would like to mention that um, we have a dedicated facility at EAG which does the moisture analysis in hermetic devices as well as in solids or in direct gases, where we directly look at mass 18 using the quadruple mass spectrometer system. So in that case, the detection limit for moisture would be much better if we directly measure as a mass. But yes, IGA can perform estimate the moisture, but we should use some other technique, well-established moisture technique to measure the moistures.
Thank you. The next question is an interesting question, and it's to be found typically in analytical chemistry based analyses. And the question is, are detection limit values materials based or instrument based? That is, can you detect the same level of sulfur, for example, in steel as you could in tungsten carbide?
This is a very good question. The detection limit value is determined by series of factors like material chemistry, what kind of flux being used, the concentration of elements in the selected reference materials, and finally, what is the sensitivity of the detector we are using. For example, this sulfur analysis, the detection limit in steel is detected by the standard, which gives us the detection in the range of, let's say, 10 ppm. However, for carbides, the detection limit value is even higher due to carbon interferences. Somehow, when high carbon content present in the sample, the sulfur detection limit may be elevated from 10 ppm to perhaps 50 to 100 ppm. The exact reason unknown, but I suspect sulfur's ability to form competitive CS2 and other sulfur species other than SO2 is the reason. Instrumental detection limits are instrumental based. Method detection limits are sample based. Method detection limits are based on sample weights and properties and release characteristics. So yes, in this, as a summary, there are several factors, and depending on the element we are looking at, we can decide the detection limits.
Thank you for this excellent explanation. The next question is, how does IGA compare to TGA coupled with FTIR?
Okay, so for combustion IR, it is only interested to detect CO2. If you are only interested in CO2 by combustion of carbon, it is done in oxygen plasma, and that does a quantitative results all the way up to the ppm level. Whereas TGIR investigates the evolved species including CO2. So it's not just limited to CO2, but it can look at other species including the organic species. So the results, but in TGIR, the results are semi-quantitative. But in case of IGA, our results are more accurate, and though it is limited to only CO2 and SO2, the results are more accurate and we can have a better detection limit if you use IGA. But when you are looking for unknown gases, then maybe TGA with FTIR would be a better choice for us.
Thank you. The next question is, it seems based on your information in the webinar that you are heating a sample along with the flux. What would happen if the flux contributes to the final gas release?
That is an excellent question. Yes. So we didn't give the minute detail into the talk, but the way it is done is that we take the flux into the crucible first, and then we heat the crucible with the flux and do the perform the outgassing. And after that outgassing, when we have the desired temperature, we basically drop the sample into the crucible. So and that time we start the measurement. So basically we are outgassing the crucible as well as the flux material before extracting the gas from the sample. But yeah, this is excellent question, a really minute detail, but I really like the question.
Thank you. So what it seems like the final answers that you get represent the ones from the sample.
Yes, yes, that is the so we take care of the the protocol where we make sure that we only collect the gas that are released from the sample, and the contribution from uh, the crucible as well as flux material would be avoided or minimized. As I mentioned on the crucible, when I was giving the crucible details, in some of the cases we pre-burn the crucible for several hours before using it in order to get rid of any gases that are absorbed from the crucible, as well as some kind of contamination that crucible might have, to get rid of those things. And of course, as I mentioned, in the standard method, we do the blank first, and blank is exactly the same procedure just without the sample. So that also gives us the baseline um, before doing the analysis. And that makes sure that we only look at the gases released from the samples.
Thank you. That helps to clarify the question. The next question is it possible to determine carbon, nitrogen, sulfur, and or hydrogen in a gaseous sample? And if yes, does EAG Laboratories has the ability to perform such an analysis?
Well, for using IGA, doing gas analysis, doing this carbon, nitrogen, sulfur, and hydrogen directly from the gas is not possible. What we can do is we need a solid material to extract the gases. But yes, at other EAG laboratories, we have this facility of doing direct gas analysis. Again, this is tie up to the earlier answer where I was referring to uh, the analysis using quadruple mass spectrometer system, where the gas is directly expanded to the quadruple system, and where we individually detect the gases. So the technique would be totally different for if you want to analyze carbon, nitrogen, sulfur, and hydrogen in a gas sample.
Thank you. The next question is, what is a typical ceramic crucible?
Oh yes, typical ceramic crucible which are used for carbon and sulfur analysis are aluminum oxides. And again, coming back to the point, they are mostly preheated before the use. We heat up to almost like 1000 degrees Celsius prior to the analysis.
Thank you. The next question is, when you use solvents, as you mentioned in your webinar, uh, does the solvent cleaning process introduce gases, and if so, how does one remove it?
Yeah, this is a good question. We have observed through our experience that the solvents do not introduce gas to the sample. If we have a sample that could absorb from the solvent, we try not to use the solvent. But yes, the in general solvent doesn't introduce any gas to the sample. And also there is a point where after solvent we do the drying, so anything sticking on the surface would also release that before we really do the analysis.
Thank you. The next question is, how does one select the extraction temperature in, let's say, a fractional hydrogen analysis in one of the slides that we showed for silicon? Yes.
Yeah, so that is of course that needs a method development, but typically that is controlled by the bonding energy. So we have to look for the certain type of expected bond in that particular sample. Like in case of polysilicon, because of that a priori FTAR study, we had the idea about at what temperature certain bonds will break and release the gas. So you need to have that a priori information about uh, to have the temperature setup. The other method is that uh, just do the normal temperature heating and look for a broad spectrum and then optimize as on the peak release peak you can see and optimize for the temperature steps. So yes, this is we don't know a priori what kind of temperature stepping would be required. What we have to do is a method development and then come up with the final set of experiment where we can confidently say about the gas release from linked with certain bondings.
So it seems like in trying to do these types of analyses, method development becomes the most important piece in determining the programs, for example.
Yes, it is, and at EAG we are proud to do that because I think maybe every after every 10 sample, maybe one sample we would get that needs a different method, and we love to do that kind of a development and come up with the solution. So yes, some samples are not straightforward, and probably I was able to show by the examples of some case studies that we do method development before that. So other than ASTM methods, we go beyond that.
Yes, and of course, with all method development projects, it is also important to validate such methods when they are developed to
Yes,
increase the
yes,
confidence levels.
yes, yes.
Thank you. The next question is, when analyzing hydrogen, oxygen, or nitrogen containing elements in the compounds, does one have to convert them into H2, O2, and N2?
Yes, yes. For the detectors, yes, there is a protocol for that. So for hydrogen and nitrogen analysis, it is converted to corresponding H2 and N2 molecules. And for oxygen analysis, it is either detected as CO or CO2. Mostly with the newer generation of the equipment, we measure oxygen as CO2. Yeah,
Thank you. Thank you.
yeah.
The next question is, how does one determine the oxygen concentrations in metal oxides by using IGA?
Can you please repeat that question? I just
Yes.
couldn't understand it. Yeah.
The next question is, how does one determine the oxygen concentrations in metal oxide samples using IGA?
Oh, okay. So
So in this case, probably in the oxide, one utilizes graphite powder to ensure enough carbon to reduce the sample.
yeah, that is one of the way. And so for oxide, we utilize graphite powder to ensure enough carbon to reduce the sample. We also have a variety of flux combination that allow us to break down oxides and completely release oxygen. And we confirm that with reference materials so that we can ensure that the release has been seen completely.
Thank you. The next question is, does oxygen not react with graphite crucible during this analysis phase in IGA?
Uh, no, oxygen will not interact with the graphite crucible. Um, and yeah, that is one of the reason why graphite crucible is being used.
Thank you. The next question is also regarding solvents. Are there a wide variety of solvents that can be typically used, and would that be a part of the method development phase in IGA?
So solvent means I think
For the
it is
cleaning during the
cleaning.
cleaning
Yeah.
phase, yes.
Yeah, we specifically use ethanol and acetone uh, because of its property, how it can clean and does not affect the sample or create any kind of a chemical reaction. So those are the main two solvents being used. As I said in one of the example that for copper matrix, uh, after cleaning the oxide layer and after etching, we put that in acetone uh, just so that the oxidation layer doesn't develop further. Um, so yeah, so we for for the established method we use ethanol and acetone as a solvent, and they will have minimum or no effect on the sample.
Thank you. The next question is about the typical ceramic crucible that is used in the analysis. Uh, these ceramic crucibles are baked to 1,000 degrees Celsius prior to the analysis.
Right.
Uh, and what is the reason that the temperature? How does one select the 1,000 degrees Celsius temperature?
Yeah, it's a good question. It is an ASTM method also that we follow, which says that it should be done. And the chemistry behind is that by baking at 1,000 degrees Celsius, we are making sure that there is no leftover residual gas sitting into this ceramic crucible. Uh, so yes, that is also defined by the ASTM standard as well as depend on the chemistry.
Thank you. During the webinar, you mentioned about the application of IGA in the ferrous industry, and that how EAG has used it for other matrices also.
Mm-hmm.
Does EAG also consider matrices that you have not highlighted in your case studies other than those?
Yes, surely, because these case studies are just the example of some of the examples where uh, we could show how we can do the method development and get to the accurate and precise measurements. But of course, as I said, and probably on one side, that any inorganic material can be analyzed, inorganic solid can be analyzed using this IGA technique. It's a question of developing a method.
Thank you. And now we will go to the final question of this live webinar series. And that question is related to the ASTM methods. Wherever possible, are ASTM methods the way to go in terms of developing methodologies?
Mm-hmm. So you are asking that is there other ASTM methods other than what we listed, or?
I think that is correct.
Yes, yes. So those are there are mostly driven by the steel industry, where this standard method are developed for doing analysis of carbon, nitrogen, oxygen, hydrogen, sulfur in most of the material related to steel industry. But as we have shown that we can do certain other elements, other kind of material also. And yes, it would be for the for this good for the community or for the industry that we can expand those ASTM methods and try to include more different kind of unconventional method into that methods. But yes, right now we can do all the STM methods that is listed, and that's our routine analysis. We haven't got any case studies for that, but yes, we can definitely do those kind of analysis on a routine basis.
Thank you, Jayesh Kumar, for clarifying that and also providing all the answers to the questions posed by the attendees.
Thank you, Rajiv.
Thank you, Jayesh Kumar and Rajiv. That was a great talk and great Q&A session. And thank you everyone for attending today's webinar on IGA. If we didn't get to your questions today, we'll be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. Once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate if you would complete the survey and provide your feedback. Please be sure to register for our other upcoming webinars in the series. And on behalf of EAG Laboratories, a Eurofins company, and our presenters, thank you for joining us today, and have a great rest of your day.